Okay, thanks. Thank you, Rosa, for that nice presentation. It's a pleasure to be here. It's a pleasure to get together again with the Mexican French project. But today I'm going to talk about the TV Skype with HAWC and GRB Physics. But I'd like to begin by saying that I am part of this collaboration. I was in charge of the data. I was a data manager for more than 10 years, since 2010. Now, I'm working in topics associated with gamma ray bursts, gravitational wave events, and active galactic nuclei. So, HAWC is an international collaboration between more than 30 institutions in Mexico, the United States, Germany, Poland, Italy, and Costa Rica. So, the HAWC detector is located in central Mexico, in the state of Puebla, between Pico de Orizaba and Sierra Negra. This detector is situated at 4,100 meters and is located at 19 degrees north latitude, of course, 4,100 meters above sea level. It covers an area of 20,000 square meters. HAWC operates day and night, providing a large field of view for the observation of the highest energy gamma rays. HAWC is sensitive to a 100 GBs, from 100 GBs to 100 TB energy range. HAWC comprises an array of 300 identical water Cherenkov detectors made of 5 meters high, 7.3 meters diameter commercial water Cherenkov tanks. Each water Cherenkov detector contains a custom-made light-tight bladder to accommodate 200,000 liters of purified water. Each water Cherenkov detector or each tank contains four upward-facing photomultiplier tubes at the bottom. Since over 90% of the events that HAWC detects are cosmic rays, they must be separated efficiently from any gamma ray signature present in the data. Due to the large transfer momentum carried by the products of the hadronic interactions in the shower, the distribution of energy is much smooth for showers initiated by cosmic rays than the showers initiated from gamma rays. So to remove a large fraction of cosmic rays, we apply gamma ray hadron separation cuts. HAWC, as I told you before, HAWC detects events in the energy range from 100 GBs to 100 TBs. The angular resolution of HAWC at 1 TB is 1.3 degrees, and at energies larger than 10 TB is only 0.2 degrees. HAWC surveys 2/3 of the entire sky when an uptime in excess of 90%, making it an ideal instrument for searching for very high energy transient phenomena. HAWC needs much higher exposure than imagined atmospheric Cherenkov telescopes. For a source similar to the Crab declination, 1 year of HAWC data taking is equivalent to 2,190 hours of observation. In other words, a source with a similar Crab declination will be 6 hours per day in the HAWC field of view. It's important to say that imagined atmospheric Cherenkov telescopes are the most sensitive, very high energy instruments, but their narrow fields of view prohibit unbiased and continuous monitoring of more than a few sources. The HAWC strengths are the sky survey, 2 by 3 exactly. Extended sources, HAWC can observe an extended sources larger than 1 to 2 degrees, and different sources at the same time. Yeah? Can observe sources of the highest energies larger than 10 TVs. In fact, HAWC detected first and reported 4 sources with photons larger than 100 TeV. Of course, all of them with galactic origin. HAWC can observe transient and variable sources with time scales from minutes to hours. HAWC is operated as a scientific instrument since March 2015, has been operated for more than 5 years as a scientific instrument. So HAWC has HAWC monitoring programs, has an online and offline searches. Yes, HAWC monitors all the sky. Yes, it has the self trigger, and 2.2 times 2.2 square degree space. HAWC uses different time windows and different transit. Depends on the object that we are going to study. For example, when we studied the Pronto mission in GRBs, the time window is divided in 390, the duration of the burst, 3 times T90 and 10 times T90. But when we study the afterglow, we use another technique. The time windows is divided in 10, yes, and depends of the burst. If there is a short, a long gamma ray burst, we can assume the time window. For example, it's a short, and each time window is just 2 seconds. We can follow up alerts, and we have different MOQ with different partners. In the offline analysis, we use Bayesian blocks to analyze light curves. For example, the extragalactic objects, Macarian 421, Macarian 541, and as I told you, different search for very high energy emission from gamma ray bursts. If we analyze the prompt, or if we analyze the long-lasting or delay emission, the afterglow, in other words. So this is the third HAWC catalog. It was analyzing 1,523 days of data. 65 sources were detected at a significance larger than 5 sigma. And this is the galactic plane. You see here the galactic plane, the extragalactic blazar, Macarian 441, Macarian 421, and the Crab Nebula. So these skies are shown with the purpose. You know, the HAWC has observed a large fraction of sources, but we are not lucky with gamma ray bursts. For the galactic plane, we put all this map again. These sky map are shown with the purpose. You know, the HAWC has observed a large galactic object. Below appears the name of the in the third catalog, HAWC catalog, and above is the usual name. Several of them have been reported by HAWC and other Cherenkov telescopes, Veritas or Magic, and different declinations, ascensions. Again, to complete this one, again, as I told you before, I show this sky map with the purpose. You know, the HAWC has been observed a lot of sources, but concerning gamma ray bursts, we have been not lucky. Yes, we are talking about gamma ray bursts. HAWC has only derived upper limits, but with these upper limits, we can constrain GRB physics. The following 15 minutes, I'm going to show you that with these upper limits, we can constrain GRB physics. So this is going to focus on gamma ray bursts. Okay, again, we have been searching for TV photos in temporal coincidence with the prone episode, with the main episode, and the afterglow. During the time, we have used different time windows, yes, and different techniques. When we consider a prompt, 3 time windows, T90, T90 again, the duration of the burst, 3 T90 and 10 T90. And we consider the afterglow, we use 10 time windows. And the T90, the time window is T90 when we consider a long gamma ray burst, and the T90 is 2 seconds when we consider short gamma ray burst. So this is the motivation. The synchrotron self-contour forward shock emission predicts emission in the energy range that HAWC operates. Synchrotron photons are content scattered by the same gender electrons. It is unavoidable. And you see in the upper and lower panels, upper and lower figures, the flux as a function of time, the light curve. The spectral energy distribution, the flux as a function of energy, considering 2 cases. The first one is when the circumburst medium is a stellar medium. Yes, and the lower one is when the circumburst medium is constant. So when typical parameters, we plot this spectral energy distribution, and you see that HAWC energy range lies in the maximum flux. So it's a nice motivation with typical parameters of gamma ray burst. So when you do some calculation in this model, you can observe that the detection of very high energy photons depend on many different characteristics. For example, that the circumburst medium is very dense, with denser than others. The burst is close, has low redshifts. The gamma bursts are powerful, are luminous. The kinetic energy, equivalent kinetic energy is high. And the most important is that the synchrotron self-contour emission is not in the Klein-Echina regime, because the flux is drastically suppressed. So, possible candidates. 1 year ago, the lab collaboration reported the second GRB catalog. In this catalog, 20 GRBs with energies larger than 10 GBs were published. So, for example, the GRB 1304-27A, the monster, one of the most powerful bursts, with this redshift 0.3, the highest energy photon, almost 100 GB, reported at 244 seconds. The second high energy event, this with an energy of 52 GBs, was reported in the direction of the GRB 160509A. Okay. Other motivation, but there are many relevant bursts in this catalog, but in my opinion, the most important are these 2. And another motivation, the recent Cherenkov telescope detection by Magic and Heath. GRB in all these cases, GRB 1901 14C and 1807 20B, 2 are missing, but there are no data yet. Yes, I'm going to discuss in the following slide. But you see that was close, not very close, but close with the redshift, and was detected below, above 100 GBs, between 0.3 to 1 TVs, and the detection in the first case was up to 20 minutes, and in the second case, the detection was in the 0.1 and 0.44 TB energy range. Have only detected 1 data point at 10 hours and put an upper limit in a time scale of days. So we are still waiting for a powerful gamma ray burst in the Hawk field of view. All of these, the last three examples explode out of the Hawk field of view. And the first one, the GRB 1304-27A, occurred when the Hawk was not complete, that was not finished and not working as a scientific instrument. But in all of them, Hawk put a constraint, upper limits. So Fermi has observed gamma ray bursts that Hawk could detect. For example, the short gamma ray burst, one of the most powerful short gamma ray bursts, and was detected with the highest photon energy was around 30 GeVs. The GRB 090510. This is the light curve, multi-wavelength light curve, and the right-hand panel, from top to bottom, you see the GBN observation. The first two, the GBN observation in both instruments. Then you see the LAT observations. The first is LAT low energy events, and probably this all events. And the next one is the LAT with energy with photons larger than 100 MeVs, and the last one with photons larger than 1 GeV.
Sí, aquí estamos.
One of the collaboration, the Hawk collaboration, excuse me. One of the collaboration, perform a simulation and extrapolate up to higher energies. Yes, and we realized that if this gamma ray burst had occurred or had been occurred today, Hawk could have detected photons with the same characteristics. Now you see the simulation in cans per beam, more than 10 photons, with photons larger than 30 GeVs. But we are not lucky. Okay, the next one, GRB 1304-27A, has been one of the brightest bursts ever detected by Swift, very close, and the most powerful gamma ray burst with a redshift less than 0.5. And the Fermi-LAT observed a very high energy photons up to 20 hours, almost 1 day. As was surprised, was awesome. Yes, and the most energetic photon ever detected at that moment, of course, was almost 100 GeVs. Nowadays, the information has changed. So the upper panel, the upper figure, you show the spectral energy distribution. Yes, you see the upper limits, black lines. You see the upper limits with different considerations and different energies. You see also the Fermi flux, and the Fermi flux is below. Is below to the upper limits. Remember that at that moment, Hawk was not completed, but that the upper limit is far away. But if Hawk would have been finished, has been ended at that moment, you can see the red dash, the green dash lines, and is below the Fermi flux. In other words, Hawk would have been detected photons from this gamma ray burst. But with this upper limit, we can do some kind of physics. This Raptor, the optical telescope, collected photons very earlier during the first 10 seconds, and this flux represent an optical and bright peak, an outstanding peak. Yes, if you consider that the first peak is produced by or is described by synchrotron radiation. And the second peak that you can build with BAT data, GBM data, and LAT data could be used the synchrotron self-contained photons. The first peak is synchrotron radiation. The second bump is could be explained with synchrotron self-contained emission. So in that case, when synchrotron self-contained flux is larger, is higher than the previous one, the synchrotron photon, you can expect synchrotron self-contained photon from second order, as in this case. So we put the upper limit, and with this upper limit, we could constrain the physics. So what we did at that moment, what we did was that LAT was originated not from internal shock, instead from external shocks. This was a simple model. So this is a work that now I am doing with some colleagues in the Astronomy Institute and Simone also. This is one example. Just we are working with more than 50 short gamma ray bursts. These gamma ray bursts corresponded to the third short brightest burst detected by GBM. The T90, the duration of the burst was 1.2 seconds. And the right hand figure below corresponds to the light curve. This is fluence as a function of time. In red, you can see the HAWC upper limits, and you see two fluxes in gray, a dotted and a dash, depending on the circumpulse density. In one case, we consider a 0.008 centimeter minus 3, and the other case 0.1. But there is no problem, the low value, because we are working with a short gamma ray burst. But you can see that in one case is allowed, yes, and the other case is prohibited. When the density is 0.1 centimeter minus 3, is prohibited because no photons were observed from this gamma ray burst. So the flux cannot be higher than the upper limit. So with this upper limit, we could constrain physics. A similar results happen with the right-hand figures. Above is the epsilon E, that the fraction energy given to accelerate the electron as a function of epsilon B, fraction energy given to amplify the magnetic field. And you see as a small region, this is allowed region, that we could reproduce the fluxes below the upper limit. Yes, for two different redshifts, 0.3 and redshift 1. So in both cases, with these constraints, we can constrain, in addition, the Bull-Lorentz factor. And in one case, the Bull-Lorentz factor is larger than 800, and the second one is larger than 600. This agree with the burst detected by LAT, the luminous burst detected by LAT. Agree with this one. Now, we're put constraints in GRB physics with 29 short gamma ray bursts. We are analyzing 2015, 2020, this year in February, but only short gamma ray burst. Okay, what happened with the recent Cherenkov telescope detection by Magic and Hess? In one case, the 1901 14C, you see the light curve, yes, and the photon energy. And the GRB 1807 20B, again the light curves and the photons. And you see the specification, the isotropic equivalent isotropic energy, the redshift, the T90 in both cases. All of these gamma ray bursts, as I told you before, release photons larger than 100 GeVs. But we are not lucky with HAWC, with the HAWC detector. Why? The first one, the GRB, for example, 1807 20B, this is the table below. The second, the energy range that we put the upper limit. But when explode this gamma ray burst, when exploded this gamma ray burst, this burst was outside, and 18 hours later, entering the Hawk field of view. And for 1901 14C, happened something similar. 15 hours later, enter in the Hawk field of view. For this reason, the Hawk upper limits are not the best, yes, but finally we derive the upper limits in each the corresponding energy range larger than 2 TVs, and in the other case larger than 7 TVs. Next one, GRB 1908 29A. It was very strange. Why? Because was photons, very high energy photons, were collected by HEF, but not for LAT.
Missing
Yes?
7 minutes.
Okay, yes, perfect. Thank you, Rosa. So the left-hand figure, you can, this is the multi-wavelength observation, and the right-hand figure above is the LAT upper limit and the hair sensitivity. You can find a suitable and appropriate set of parameters, density, epsilon B, epsilon E, and you can calculate the flux, the synchrotron self-contact flux, and again with an appropriate parameter, the flux is below the upper limits, the LAT upper limit, and above the hair sensitivity. Of course, this is an assumption. Why? Because Hess data has not been published yet. This is very, very, very strange that more than 1 year ago, several groups around the world were working on this gamma ray burst, but nowadays there are no Hess data, and there are many, many different characteristics to the previous one. You see here, and it seems that the scientific community, GRB community, forget this gamma ray burst. But I remember the saying, the proverb, they say that those who forget their own history are condemned to repeat it. Yes, in this case, those who forget their GRB history, in that case, are condemned to repeat it. Why? Because 1 month ago happened the same gamma ray burst was detected by MAGIC telescope one month ago. A hint with signal with significant LIA 3 sigma, but LAT didn't report any upper limit, any detection. So there are only upper limits. Okay, but the similar to the previous one. So I think that there are physics behind of that. But just to inform you, all of the previous one and this one were outside of the Hawk field of view. And finally, just I'm going to show you the gravitational wave events. And there are more than 10 gravitational wave, circular gravitational wave events reported in GCN circulars. When this event happened inside the Hawk field of view, Hawk has reported upper limits. Yes, and all of them are different, several upper limits. But of course, you know that there are not optical and X-ray and gamma ray observation. So there's upper limits in all of these cases. Only in the GRB, the merger gamma ray burst, GRB 1708, 17A, and will follow for more than dozen ALICE from LIGO and Virgo. Everyone, I think that everyone put a telescope and put upper limits. You know the famous paper. And when this event was outside of Hawk field of view, at the time of the alert, we observed 9 hours or 9 hours later, this emission entered in the Hawk field of view, but only a 6% of the region. We're not lucky. We were not lucky. We derive upper limits in this range, 4 to 100 dB. Nowadays, we put upper limit in the right figure below. You see the light curve. Using a different technique, the upper limit, the time we divided in several time windows. Each time window corresponds to 1 day, yes, and put the paper is in preparation. And one task that we can do is calculate the synchrotron self-compton from the X-rays exactly, and the synchrotron self-compton in the HAWC energy range is far below from the upper limit. Yeah, so it's okay, but it's far below. So this is my summary. Finally, this is my summary. You can read it. So we present the upper limits in all of these cases. Yes, we are not lucky when we talk about gamma bursts. Yes, many of them occur when outside of the HAWC field of view. And the first one, the JRB 130427A, occurred when HAWC was not complete as a scientific instrument. So HAWC continues to monitor the whole sky in search for signatures from potential burst candidates. We're waiting for a big gamma ray burst in the HAWC field of view. Thank you, everyone. Thanks for listening carefully this talk. Questions, suggestions are welcome. Thank you, Rosa.
Thank you, Nissim. I don't know if you have questions. This is the moment.
I have a very simple question. First, it was very nice, very clear.
Thank you.
Again. And what is the future of HAWC? How long you plan to operate? What is your plan?
To operate with HAWC?
Yes. What is the status in the future of the instrument?
Okay.
For a long time.
Yes, HAWC will work for 10 years more, up to 2025. Yes. HAWC continue to receive alerts and could follow alerts. Yes, it's usual. Not only gamma ray bursts, but neutrinos and gravitational wave events. Will be operating for 5 years.
We can hope to have the one will be launched in June 2022. The first alert will be sent if the schedule is we expect the schedule. The first alert we can expect to have the first alert in September 2022. So at least for several years we can have joint observation, which is it's nice.
Okay, thank you. It's important. Okay. HAWC operates at is located at 19 degrees north latitude and is operated for 5 years more. But now we are working on the HAWC South. We are looking for a new place, probably in Argentina, probably Bolivia, probably in Chile, yes, or in Brazil, to work at the South Hemisphere, yes. In order to yeah, exactly. In order to share observation with CTA, like a North and South Hemisphere.
What are the chances of success to have HAWC? Well, you have the budget, and if yes, when you plan to have the first observations?
Now we're discussing. We are doing simulation. We are doing simulation now in the South, for the South, HAWC South. We're discussing about the place, the site.
Okay.
2 weeks ago, we discussed about we meet together with many people, several people around the world, not only Mexican, Latin American, European, and so CTA is very expensive. CTA is very, very expensive. And if I understand correctly, several governments don't support this kind of project. HAWC South is cheaper in comparison with CTA and satellites. So many countries are joined together with this project, HAWC South. So it's a promise project for the future. We'll probably working as a scientific project in 5 years, 4 years probably.
Okay, okay, it's interesting. Thanks.
Thanks to you for asking me.
More questions? I have just one, maybe a very simple question about the time of reduction of your data. How much time do you spend before you have the upper limits? Or how is the process?
Depends. There are two analyses: one-line analysis and offline analysis. When we analyze the information online, I think that a pair of minutes, hours, yes, you can obtain the upper limit. But okay, but of course, it's not as good as when you think the physics, when you think better the situation, you can divide, accumulate, put cuts on separation, gamma hadron separation. The background is separated also, or increase the statistics. You can use different techniques to increase the statistics, and this is offline. And the method that you could use, and you could derive in 1 day. No, in 1, 2, 3 days, depends on the person. If you're a Mexican, it's quickly. No, depends on the person. But the problem is, when it's online, you can analyze the data at the site. This is between Sierra Negra to Pico Orizaba. This is 4 hours by car. So when it is offline, yes, usually a person has to go up the mountain, copy the data, back again to the UNAM, and if we are going to analyze data, of course, no problem. But if someone else is going to analyze data in US, we start the data transfer, and the data transfer depends on the size. Could be spend more than 1, 2, 3 days. That all data is transferred to the Maryland University in the cluster, other cluster.
Thank you, Nissim. And finally, Diego.
Hi, Nissim. So during the pandemic, what has HAWC's status been? Like, has it suffered any contratiempos, counterparts?
Look at it. No, no. You can see that we could find bad time about that, but no, was not the case. And also, always a person will go up to the mountain. Just what the pandemic said that 2 persons cannot live together more than 1.5 meters, but 1 person can go up and bring up the data. The data, the arrays, each array has 15 terabytes of data. This is the data accumulated for 2 weeks, and bring back to the UNAM connected in the nuclear cluster. Just you need 1 person to do that. Yes. And the status nowadays, I knew that Magda's husband, Ruben, and other guy from Mexico went up to the mountain one week ago. Yeah. And of course, they were together at the same Karen.
That's fine. So it's good to know that HAWC didn't have any setbacks with
No. Bueno, we're lucky because no instrument has been damaged because in the past lightning have damaged many instruments and or the transformers. When the transformers are damaged, personnel from the electricity here in Mexico have to arrive, and of course, if this have occurred, probably 2 or 3 weeks takes time to that the person went up and fixed the problem, but was not the case for
Okay.
fortunately.
Good. Thank you.
My pleasure, Diego.
Is there more question?
I'm going to change here.
Okay, si no, thank you very much, Nissim.
And for giving me the opportunity to give a hot talk.
And finally, for this meeting, I just want to know your feedback